All right, welcome everybody to week 9, day 1. We're going to be talking about a few very important concepts today. The first is motivated by the linked list competency exam take 1, which we did not have good results on. And by we, I mean you guys. Don't you hate it when professors do that? Well, it seems like we're having trouble understanding. No, no, no. It's, it's just you. So let's go over the linked list competency exam, and we need to talk about the notion of a copy constructor, because we talked about it once several weeks ago and didn't touch it again. And guess what? It was on the competency exam, and only like 10% of people got it right. So it's yeah, because like the teachers are trying to be like, less like blaming people. Like we got it wrong, and it just comes off as very like condescending. You know what I mean? So the linked list competency exam take 2 is now up. It's due in a week, so don't worry too much about it if you failed this one, because you get another shot. So as you can see, the grade's not good. So if you didn't do well on this, by the way, don't beat yourself up. Most people did badly. And the competency exams are not supposed to be easy either, in part because you can retake them, so I don't feel bad, like kind of putting the screws to you a little bit, you know what I mean? They're a replacement for midterms and finals. They're not, supposed to be easy. Okay. And, yeah, let's just go through it. So, this for loop we talked about as an example several weeks ago. And the really suspicious thing about this is that it actually works most of the time. It's hard to tell when there's no compiler to tell you what's wrong. Yeah, it's not a compiler error. It'll compile fine. And the worst part is it'll work fine most of the time. So what's going on here? We set a temporary pointer equal to the head, so we're starting at the top of a loop. We're going until temp is null, going forward through the list one node at a time. So this is your standard list traversal algorithm that all of you should be well aware of. And we are freeing the memory at each node as we go down. I wish it was as simple as this to delete a linked list. It is not. And the reason why it is not is because once you've deleted a pointer, actually let me back up even further. What happens when you say delete a pointer? The pointer itself doesn't change. Remember, a pointer is just a memory address. It's an integer. So when you say delete 42, it doesn't change the pointer at all. The pointer still has the number 42 in it. And it doesn't change what's in RAM at address 42. Neither of those things happen, and that's probably the number one, like when you have your mental model up here in your mind, when you say delete a pointer, you're thinking the pointer is going to become null. Or you think that the RAM of that address gets erased or something like that. All that happens when you say delete 42 is that somewhere inside of the memory allocator, there's this big data structure called a heap that kind of used to be called a heap. It doesn't matter. There's this big thing, and it just finds that region in memory at memory address 42, and it marks it as being available. Before, it was marked as being reserved. Nobody else could touch that memory. It's yours until you call delete. Once you call delete on it, a little flag is set, a Boolean flag is set, and that flag says that memory can be reused by the next new call, maybe, or not. It just can be reused. That's all delete does. It's a very simple thing. It doesn't erase the RAM, it doesn't change the pointer, it just marks that region of memory starting at address 42 as being available. So, the really scary thing is this code will probably work, because it didn't change what's in RAM. So when you say delete a node, you actually can say temp equals temp points to next, and it'll go to the address 42 and look up the next field and go to that spot, and this will actually probably work, and this is terrifying. It's not. It's like deleting a file. Yeah, when you delete a file, it doesn't actually erase it off the hard drive. It just marks that region as being available. And so maybe a week from today, somebody will make a new thing and it'll overwrite it. But until that happens, your data's still there, and that's how like disk recovery works and things like that. So this is using temp after it's been deleted. This is called the use after free bug. So you're deleting temp, and then at the bottom of the loop, you say temp equals temp points to next. You are accessing the memory from temp after it's been deleted. That's a no-no. That's a big no-no. It's an error. Okay? So, can you download more RAM? So, so the scary thing is your code will probably work, and it'll probably pass all your test cases, and you're like, yay, cool, I know how to delete a linked list, and you're wrong. Because you did it wrong, right? You have to make a copy of the next pointer, then delete temp, and then set temp equal to the copy, and whatever. And your code might be fine for 20 years. And then 20 years from today, somebody comes along and multi-threads your code. Multi-threading means you have multiple flows of execution within the same program. And then maybe you call delete, and in between the time you call delete and temp equals temp points to next, the other thread calls a new. This is called a race condition, okay? And this is why why your code has to be like good to be multi-threaded, because it'll discover problems like this. So you call delete over here, and then the other thread calls new, and the new chooses the RAM that was just deleted, and it wipes it and puts in some other random stuff in there. And then the other thread goes and reads from there, and it reads that 0 as the next, and it segfaults, and all hell breaks loose. Okay? So your code crashes, and you have no idea why. Right? That code works. It's perfect. It's been tested for 20 years. It works fine. Yeah. That's why address sanitizer is so important. You should always develop your code, write your code with address sanitizer turned on. Don't wait until you got a million lines of code, because guess what? Address sanitizer is going to find a million bugs in your code. Okay? Address sanitizer is only about 6 or 7 years old, maybe, something like that. And it's a game changer. Before that, you had to do something called valgrind, and valgrind is a separate tool. You would type valgrind a.out, and valgrind would run your program and search for memory leaks and things like that. And it was a real pain to use. And the reason why it's a pain is because things like the standard library leak memory, true story, and they do so deliberately. And the reason why the nuclear system created 20 years ago, did you know this? The standard library actually leaks memory intentionally. It allocates memory, it has a new, and it does not have a delete. Do you guys know that? It's quite intentional. Because, like, let's say that you allocate memory for cout. And your program is exiting, it's quitting, it's going away, and now's the time to delete cout or whatever, you know? At that point, the standard library is like, we're dying anyway. Why bother, you know, calling delete? It takes time, right? Let's just make it faster to quit. And it just like leaves this stuff in RAM and just quits because it knows the operating system recovers all of the RAM anyway. So it's kind of like, you know, when an old person's dying, it's like, hey, do you want me to, you know, I don't know, you know, tie your shoelaces or something. And they're like, who cares? I'm dying anyway. You know, it's not like I'm going to walk anymore. You know, there's something depressing, huh? And so they just don't. So they just don't bother. Yeah. Darth Sidious would not be happy with violating the rule too. Yeah. Yeah, but here's the thing. Valgrind detects that, right? So you run Valgrind on your program, and it's like, you leaked 195K of RAM. And it does tell you this, and then you're like, what, where? I wrote hello world, and it's actually in the standard library. And so Valgrind, and then you have to like configure Valgrind to like ignore certain memory leaks and not others, and it's kind of annoying to use. Whereas address sanitizer just will be like, right there, you just include it, your program runs normally, and if you ever screw up, right there's your problem. Line 35, you screwed up. Okay. So, plain English, what is this code doing? Do you still remember how to use Valgrind? Sure. Yeah, okay. So I'm going to new 4K of RAM, also known as 1000 ints. Not deleting it. Okay. All heap blocks are free. That doesn't seem right to me. Or if that got optimized out or something. There we go. I think the optimizer removed that. It's one of the problems with the optimizer is that it changes your code, and you're like, So there we go. So in use at exit, 4,000 bytes in one block. You see that? So Valorant grind. Yeah. And so right, we allocated 1,000 ints and we didn't delete it. So it tells you there was one block, a contiguous block of RAM with 4K. You did 3 LX, you did 2 freeze. I think I've already got this thing ignoring the standard library problems. And then I'm also using uninitialized values, right? Because this RAM here is not initialized, and I'm outputting uninitialized RAM. And so Valgrind also detects that. So you are using uninitialized RAM. Okay. So I definitely lost 4K of RAM, and yeah. And then you can put a flag on to main.cc line 8 uninitialized value created. Yeah. Okay. So yeah, you can see it's a lot less useful than address sanitizer. It kind of runs, then after your program finishes, it tells you what went wrong. Whereas with address sanitizer, let's do this again, -f sanitize equals address, debugging on, main.cc. Address sanitizer, just the second that you do something wrong, it kills your program. It says right there, you leaked 4K in one block, called new, on line 7 of main.cc. Done. So, currently non-initializes variables. I did so deliberately. Okay, so there you go. Got some uninitialized RAM. Now if I put on -f sanitize equals task failed successfully. Find. Didn't detect it. Yeah, ubisan isn't that good, honestly. Ubisan's not that good. Okay, so yeah, so address sanitizer much better than Valgrind. All right, so in plain English, what is this code doing? Print list, linked list pointer node. It's okay. So the first thing you see a pointer. What is the first thing that should pop into your head whenever you see a pointer? It has colors, yes. Address sanitizer does have colors. Check if it is null. Yeah, exactly. Are we checking to see if it's null? No. So there's a possibility right off the bat, because that little arrow there, anytime you see that arrow, you got to be like, what if that thing was null? We have no guarantees. That could be a seg fault. As it turns out, though, it's not just a possibility of a seg fault. It's a guaranteed seg fault, because even if this one's not null, it'll go to the next and go to the next and go to the next and go to the next until it is null. And so this is guaranteed to seg fault at some point. Okay? So it is a guaranteed seg fault from dereferencing a null pointer. Is it printing out all the nodes in the linked list? Yes, but not successfully. We need to have an if null check on there. If node is null, return. And this is a recursive print, by the way. Anytime you have a data structure that exhibits the self-similarity property, in other words, a sublist is a list, a list with just one node in it is a list with 10 nodes is a list with 100 nodes is a list. It's a recursive data structure. And so anytime you have that, writing recursive code is usually very simple and clean. And we'll see another example of that later in today when we talk about binary search trees some more. So what operations are list faster at than vectors? So most of you are pretty good at this. The trouble is that these 80 to 90% of people were different for most of the answers. So linked lists have order 1, push front, push back, pop front, pop back, right? For your standard doubly linked list. Okay, got a head, you got a tail. You can just add to the head. Even if you have a billion people in a linked list, you can add to the head and just constant running time. You can delete from the head in constant running time. You can add to the tail in constant running time. You can delete from the tail in constant running time. And that is a place where it is better than vectors, because vectors are order 1 in the back, but they are order n on the front, because every time you insert at the front of a vector, you have to move everything to the right one. So if you have a billion elements, you have to move them all to the right a billion times. And if you delete from the front, you have to move them all left a billion times. So linked lists are definitely faster at inserts and deletes from the front. They're also faster at inserting and deleting to the middle if you have a pointer there already. Now, the problem is, like, how do you get a pointer to the middle? And that's an order in operation. So in practice, it doesn't really help most of the time. But if you do have a pointer there already for some reason, like you just did a find operation and then you want to delete it, it is faster to delete from the middle of a list, because you just delete the thing and have the pointers on either side go like this and point at each other, and it doesn't matter how many billions of nodes there are in the list. You just cut it and splice the pointers around it, and it's order 1. Printing out all the elements is order n for basically everybody. Okay, this is the one that got everybody. So, does the vector not have to move all the right elements over after? If you delete from the middle of a vector, it does. So if you delete from the middle of a vector, and you have a billion elements in the vector, you delete an element there, it's got to move half a billion elements to the left. You might be like, but wait, that's order n divided by 2. No, we don't care about things like divided by 2. When it comes to big O, it's just the shape of the curve, right? And so if you have an n divided by 2 and order 2n, order 3n, order n divided by 3, doesn't matter, it's all order n. It means linear. It's got a linear relationship. So deleting from the middle of a vector is order n. Deleting from the middle of a linked list is order 1. Okay, so the copy constructor, though, is what we want to talk about. And so let's pull this up. And let's talk copy constructor. So a copy constructor is needed because what happens if you don't make a copy constructor is that C++ will make one for you. And by default, it just copies all the values over. And so here's the problem. If you've got, and you know, we'd have lots of stuff here, right, for our list class. The problem is this. You've got a pointer for head, and you've got a pointer for tail. If you set one list to another, so for example, you got a list A and a list B, you say A is equal to B. What happens if this calls the operator equals, not the copy constructor, but it's basically got the same problem. What happens is this, and it's bad. We have talked about the rule of 3 and the rule of 5. I guess we can talk about today. Rule of 3. Anytime you're messing with memory, pointers, new, delete, etc., you need what? Anyone remember the rule of 3? And I'll show you why. What happens with the default ones is that you've got, you know, list A over here, and it's got like a head, and you got like some list or something. You got a tail. You got list B over here. It's got a head, a tail. What happens with the default operator equals, or the default copy constructor, is that when you say A equals B, all it does is this. That's a horrible B. Let's try that again. We say A equals B. What it does is this. It says A dot head equals B dot head, and A dot tail equals B dot tail. That's all the default copy constructor and the default assignment operator do. And for regular pods style classes, it's fine. It just copies all the memory elements over. It's not a big deal. What happens then when you work with pointers is that A's head is now pointing here, and A's tail is now pointing here. This memory, for the assignment operator at least, would get leaked immediately. There'd be no way of finding it again. And now you've got a problem where B's head and tail are pointing at the same thing as A's heads and tails. So any changes you make to A will be reflected in B. Any changes you make in B are reflected in A. And even worse, when B goes out of scope, it deallocates. Now A is pointing at deallocated memory. When A goes out of scope, it tries double freeing these things and it crashes. Okay? You basically have to always follow the rule of three. So, job Cabrera, you need three things. You need a destructor, you need a copy constructor, and you need an operator equals. Okay. And the reason for that, like I said, when you do this, this is essentially just going to be saying A dot head equals B dot head. And now they're both pointing at the same place. It doesn't do a deep copy. You need to do a deep copy, which means you want to copy all of the elements from one into another. And so what we want is something like this. List, const, list, ampersand, other. And a lot of you didn't get the signature right. Look at the signature here. Okay. That's how you do a copy constructor. Okay. And what you basically need to do is this. For linked list pointer temp equals other dot head, temp equals temp points to next. So we are traversing. This is your classic list traversal. So the pointer is we're gonna create a new pointer that's pointing at the other person's head, and we're gonna go down the list until we get to the bottom. So what we want is to go through every element in the list and copy it into us. Okay, you don't want to just have the pointers point, because now it's gonna explode. It's gonna cycle. And cause trouble along the way. So the easiest way of doing this, like let's say we've got the other parts of this class done, we would just be like push back other dot temp points to data. That's it. That's a functional. I haven't written the pushback class function yet, but assuming you have one, just do that. Okay. If not, then you just write your own little like head equals new linked list with temp points to data and new old head. Okay. Either way, same thing. That's it. Can't use a dot operator. No. For here, yes, yeah, because this is not a pointer. That's a reference. Okay. References are pointers that aren't pointers. They're literally pointers. Like whenever you have a reference like this, it's literally a pointer. It just acts like a regular variable. Yeah. So, yeah. Yeah, your copy constructor looks good. And a lot of the times when I make a class that uses the rule of three, the most common thing I do is just this. So I just delete it. Because, usually I don't want my things copied. It's kind of weird. Okay. So this is the assignment equals operator, right? So let's do this. Let's list A, and we can say list B equals A. Okay. These curly braces. There we go. Okay, so list A. Yeah, we need to have a default list constructor. There we go. Okay. So this calls the default constructor, and this calls the copy constructor. Now, There's one other place where the copy constructor is called. And then if we did this, A equals B, this calls operator equals. Remember, constructors only get called when a variable is made. A constructor is only called when a variable is made. If you try doing something like this afterwards, that's the operator equals. And it's going to be pretty much the same as the copy constructor, except you have to handle the possibility that you exist already, right? Like you might already have nodes in it, in which case you have to free them all and then do this here. I like to delete that one too, honestly. It depends on what I'm doing, but just a lot of times, like, it just doesn't make sense to even copy them. So I'm confused. Do we need to put delete anywhere? Yeah, you also have to have a thing. You have to have a destructor, right? And so you say for So there is a working list destructor. Okay. Or you can do it Minkrelli's way. Doesn't matter. You have to make a you can't both delete something and use its next pointer at the same time. So you have to. But if you move it to the next, then you can't delete it. So there's kind of a chicken and egg problem that is resolved by just making a copy of either temp or temp next, one or the other. So that is a destructor. That is a copy constructor, and then we would need a operator equals as well. Minkrelli asked me to talk about the rule of 5 today, so I'm just going to do that real briefly. Rule of 5, which is add to the above a move constructor and a move assignment operator. And so you don't have to know this for this class. It's just an optimization thing. But let me show you why the rule of 5 is so cool. Let me just delete all this code I wrote, because why not? So let me do this. Vector of ints named foo. And inside of foo, we're going to make a vector of ints named Bob. And Bob is going to be initialized at 10, 20, 30, 40, 50. Same example as in the previous class of Minkrelli. Forgive me. Return Bob, like that. And then out here, we are going to say vector of ints named Alex is equal to foo. For every integer in Alex, see out that integer. So do you guys concur that this is going to print 10, 20, 30, 40, 50 to the screen? Thanks. You guys see that? We're making a vector. We're returning it. It's going to return a copy, right? And then Alex is going to be set equal to that copy of Bob. And then for every element in Alex, it prints it out. What do you guys think? Okay. A lot of silence, so there we go. There's the numbers. Now, what's going on here? Prior to C++11, what would happen is this. We make Bob. So we take the time to construct Bob and push it back a bunch of times. And then when we return Bob, we're returning a copy. So we have to duplicate all the elements, right? And then Bob gets deleted. And so we have to do an order in copy out and an order in delete of all the elements in Bob. Then at the end of the day, Alex is set equal to the copy, the clone of Bob, and the original Bob is dead. And then we print out all the elements in Alex. Now, see if you can figure out why this is unoptimal. Step 1, clone X. Step 2, delete X. Step 3, use the clone. Why is this inefficient? Why is there a more faster way of doing this? Duplicate all the elements in Bob, delete the original, use the duplicates. It's repetitive, it's cloning. What's the faster way of doing this? If you're going to delete the vector anyway, you can just pass Alex by reference. Yeah, I get what you're passing Bob, but yeah, I kind of get what you're getting at. Just use Bob, precisely. So here's Alex equals Bob, exactly. And so what happens is this, when you have a move constructor. A vector essentially looks like this, okay? So vector is essentially, behind the scenes, it's just a block of memory. It's got a pointer to the beginning, and then there's also like the size and like the capacity and some other stuff, but this stuff doesn't matter. Basically, a vector is kind of a pointer to a block of memory, okay? And so we got here Bob, and Bob's got inside of here 10, 20, 30, 40, 50, and then probably some unused space in here as well. And so what we were doing before is that we would create a new array, copy all the elements over 10, 20, 30, 40, 50, and erase the original, and end up with essentially the same thing, just with more steps. Now, here's how a move constructor works. So a move constructor works like this. So we're constructing Alex. Okay. And Alex comes into existence at the exact moment that Bob dies. And the compiler can detect this. This is a very common thing to do, by the way. Like when you return a value out of a function, that's the moment of death for Bob, right? We're cloning Bob and then we're killing Bob. And so rather than cloning Bob and killing Bob, it pulls a sneaky. And this is what it actually does. So Alex has this R pointer, and so it just points Alex's R at Bob, and then Bob goes away. And so this is all moved inside of Alex. That's why it's called a move constructor. So Bob has an array pointer, Alex just copies the array pointer, and that's it. There's no duplication, there's no deletions. It's a single operation, basically. My array pointer is pointing at what you were pointing at. Bob goes away, I've got his memory now. It's like it reaches into Bob and steals Bob's guts and puts it inside of Alex, and none's the wiser. And we know this is okay. We know this is okay because Bob's dying, right? It's like Bob's on his last legs, and you chop his heart out and use it in a heart transplant. I don't know. I've had a lot of dark metaphors today. Okay. So, yeah, rip Bob. Alex equals Bob. Does that make sense, Portnoff? Like, so basically, you just, inside of a vector, you got a pointer to the start of the array, and what you do is you just have Alex's pointer just point at Bob's start of his array, and then Bob goes away, and we just own that memory now. Order 1 instead of order n and order n. Right? So this move constructor and the move assignment operator, these are both going to do the same thing. They just play these little pointer tricks, and they just basically steal the internal data structure out of the other one. Nice. So this is actually a order 1 operation here. Nice, right? So yeah, it's actually good practice. And a lot of people used to like pass out pointers and things, like they would new memory and pass pointers back and stuff like that. And it got really hard because if you new memory and you pass a pointer out, then whoever it is that gets that pointer is now the owner of the memory, and they've got to remember to delete it. And a lot of times when you call a function, you don't know if you own the memory or if you're just like looking at the memory. Who's responsible for deleting it? I don't know. When you do something like this, the vector itself knows. And so when Alex goes out of scope here, it frees the memory. And there's no chance of a memory leak. There's no double free risk. The container just handles it all for you, and it's just really nice. So, Alex wants revenge on Foo for killing Bob. Yeah, it's John Wick. Okay. Okay, you all understand the move constructor. I'm not going to have you write them. I'm not going to test you on them, but just like from a C++ general knowledge thing, beware that whenever you return a vector and catch the result like this, it actually doesn't have any real cost to it whatsoever. It's nice. Okay. And in fact, when it does Bob here, it might even just construct it directly in place here. I think there might be an optimization for that as well. Okay, it's called like in place something or other. I don't remember the name of the optimization. But sometimes, yeah, the actual RAM for Bob would actually be Alex because it knows that it's coming out. Any questions? Rule 3, rule 5. Copy constructor. We're going over recursion right now, actually. So here's our code from last week. So we got our tree class. The tree class has this private class inside of it. It's class within class. Yeah, we're going to go over this in just 1 second. So we got here an insert function. And so we need to do search, we need to do erase, and we need to do print. Yeah, so here is a copy constructor. Again, that's the syntax you have to learn to do a copy constructor. Oh, yeah, this is also important. So the other time, like I said, there's 2 places where you call a copy constructor. One is like when you say, you know, A equals B or whatever. But it also does it if you ever screw up, or maybe you do this intentionally. If you ever screw up, though, because it's probably a screw up. If you ever pass something by value, it calls the copy constructor. Okay. So if you remember the general rule is, and anytime you have an object like something of class type, the general rule is always pass it by const reference. If you need it to change, just pass it by reference. If you ever pass it by value, which a lot of people do, just because they think call by value is easier or something, this will duplicate the entire list. What's interesting in a deep copy and a regular copy? The shallow copy is this. When you just had A's head equal B head, A tail equal B tail, that's a shallow copy. Now your linked list is all screwed up because you have 2 different pointers pointing at the same thing, and they're going to be trampling on each other. That's a shallow copy. A deep copy says go through every element of B, and you had 10, you had 20, and then copy it into A. So you have to do an order n traversal, going through every element of B, push backing into A over and over again. That's a deep copy. A shallow copy is when you just copy the pointers over. Guaranteed trouble. Anytime you mess with pointers, you need to do a deep copy instead of a shallow copy, or you just delete it. Which is what I do a lot of times when I'm lazy. Shallow copies just creates a pointer to the same list, yes. Whereas deep copy creates completely new nodes, yeah. Rather than copying the pointers, you copy the entire everything in the list. You go and do a full traversal and copy each node, the value of each node, and you don't copy the pointers, you copy the values. That's a deep copy. A deep copy is when you copy all the values, you don't copy the pointers. You almost never want to copy a pointer from another list. The exception to that is something I mentioned in the previous class, which was if you're merging lists. So this is actually something linked lists are good at too. So if you have 2 different data structures here, like this, you have A and B. If you want to merge them together, you can just have the tail of A point to the head of B. Now you've merged them in order 1 time. So linked lists have a power of order 1 merge, and that's pretty much unique amongst the standard container types. It's called fast splicing. You can just glue 2 different linked lists together in order 1 time. You basically just say A dot tail points to next equals B dot head, and now you got 1 linked list. Easy. Pretty much every other data structure other than linked lists, you will have to copy all of the elements of B into A. Right? If you're going to merge two vectors together, you go through all of the elements in B and call pushback over and over again on A. Same thing for basically everything. So that is another benefit of linked lists. Still not enough to rescue them from their problems, but you know, if you're doing a lot of merges, you know, it's there. It's there for you. Order one merge. It's probably important to talk about. Okay. So we got a shopping list. We call the copy constructor here. This duplicates. It goes through every element of shopping list and pushbacks them into my list. So when I add 4 to my list now contains 1, 2, 3, 4. And if I were to call print list passing in my list, this also calls the copy constructor because it's called by value. Bad. Okay, so it's going to duplicate all the elements of the list and then throw the duplicates away. It's terrible. All right, so let's get into binary search trees. So we have here a tree called Google for some reason. I'm not sure why I called it that. We're inserting a bunch of things into it. We do need a search function. So let's maybe do that first. So searching, like I said, is very similar to inserting, right? So if we're going to search to see if the number 10 is inside of there, what's the first thing we do? Whenever we work with pointers, what's the first thing we do? I'm going to be searching through a tree. Do I have any guarantee there's stuff in the tree already? Hell no. So we have to first say if root is null. So if we have an empty tree and we search for 50, is 50 in the tree? Do we return true or false? Yeah. Root's our pointer. Every time. Just got to drill that into your head. Always check for null before you use the arrow operator. False. Yeah. So if we search for 10, it's not in there. There's no tree at all. Okay. Then after that, we're just going to do a little linked list pointer temp equals root while temp is not null. Okay. So now we're going to go down a tree, and so let's just pull up a picture of a binary search tree. I don't want to sketch it. Okay, there, that's better. Okay, so let's say we're trying to find the number 13. Okay, so when we start off, temp is going to be pointing at root, right? So the first thing we have to do is check to see if we have a match, right? And so if temp points to data equals the data we're looking for, congratulations, you found it. True, it's in the tree. If not, if temp points to data, or maybe I want to do it the other way around. If data is less than temp points to data, let's do it this way, for symmetrical purposes, then temp equals temp points to left, else temp equals temp points to right. So that's basically our tree traversal here. Basically it. It's one more line of code we need, but let's see what's happening here. So we got this tree over here. So we start off, temp is pointing at 10. Let's see if I can write on this. Can I write on you? No. Right on you. Sakura mochi. All right. You search inside arrays. Yes, you can. In fact, I would search for it to see if it exists, maybe. It's acceptable, maybe. Let's open this in Paint. Okay. There we go. So when we start off, temp is here, pointing here. Okay, so we're searching for the number 13. Okay, searching for the number 13. Is 13 equal to 10? Nope. Is 13 less than 10? Nope. So we say temp equals temp points to right. So temp will now point to here. Okay, come up to the top. Is temp null? No. Is 13 equal to 15? No. Is 13 less than 15? Yes. So temp equals temp points to left. So temp is now pointing here. Okay. Is temp null? No. Is 13 equal to 13? Yes. Return true. We found it. Now let's say we were searching for 12. It would go temp equals temp points to left, temp equals temp points to right, and we're off the edge of the world. Temp is now null. So there's one other thing we need to do here, and that is to return false if we hit null. And that is that. That's a fully operational search algorithm. Yep. What do you call it? Oh, it's a node pointer instead of a LFS. There we go. So that's an operational search. Let's just see if it works. Cout bool alpha google dot search 10. Let's do it at the bottom here. Search for 10. Search for 1. Search for 20. Search for 30. True, true, false, false. Good. Probably should have put an inline there. Good enough. It works. Now, any questions about this style of traversal? Basically, this is if you understand this, you understand binary search trees. It really just kind of boils down to this. Okay, and we're going to do recursion in a second, but which is the other way of traversing. This is sort of the classical way of traversing a tree. You basically go left, you go right, depending on which direction you need to go in. And eventually you either hit the thing you're looking for, or you hit null. For insert, if you hit null, well, that's the spot we're going to insert. Okay? So if we ever hit null, that's the spot we insert. On a search, if you hit null, well, it's on the tree. Okay? That's kind of your classic going down a tree kind of algorithm. Can you merge two trees? Not like a linked list, right? You just say for every element in the tree, insert it into the other tree. You could probably get away with it if the trees have non-overlapping domains, right? So like if one tree is like from 1 to 10 and the other tree is like from 40 to 50, you could attach the 40 to 51 on the bottom right of the first tree. Does that make sense? So like if they're not overlapping at all, you probably glue it onto either the left end if it's smaller or the right end if it's bigger. Right. Yeah, you could do that. The tree is going to be very unbalanced now. I probably wouldn't. I'd probably just go through every element and just insert it. Yeah, you have to check for duplicates, and yeah, it's. There's definitely some circumstances where you could do that. Yeah. Are we going to do more BST visualization in this class? Yes, we are. It's a homework assignment. Okay. So that's search. Let's talk about printing a tree. And so this is actually one of what I consider one of the most beautiful algorithms in computer science. So we want to print the tree. Okay. And so we're going to do so recursively. And so when we call print, we are just going to call print node on root. So we're going to say start at root and print the whole tree. So print node fellow here takes a pointer, and it prints the tree at that point. So if we have a binary search tree like this, and we pass it a pointer to 7, it's going to print out 6, 7, and 9 in that order. It'll print out the tree in sorted order. Okay? And so no matter which pointer you give it, like if you pass it 13, it'll print 11, 13, 14. If you pass it 11, it'll print 11. If you pass it 10, it prints the whole tree. We can do this recursively because a binary search tree exhibits the self-similarity process. Each subtree is a tree, and each subtree of a subtree is a tree. And so the same algorithm will work on a subtree as on a medium tree, on a big tree, on a gargantuan tree, etc. So here's how we do it. First of all, whenever you work with the pointers, you know the routine, check for null. So if you say print a tree and you pass it a null pointer, you just return. We're done. Okay, cool. Now, here's the magic. So if you want to print out 10, let's say, you have to first print everybody to the left. Then you print the number 10. Then you print out everybody to the right. And that is our code here. Print everybody to the left. Print my value. Print everybody to the right. Done. Seems like magic, doesn't it? Especially if you ever try tracing out exactly the path that this thing's going to take. It's going to start here. It says print left tree. Okay. We come here, print left tree. Okay. We come here, print left tree. Okay. Come here, print left tree. Null. Return. Print 1. Print right tree. Return. Return. Print 2. Print right tree. Print left tree. Null. Return. Print 3. Print right tree. Null. Return. 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 Print 5. Print right tree. Print left tree. Print left tree. Print 6, print right tree, return. Print 7, print right tree, print left tree, print 9, print right tree, return, 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 10. Yeah. Recursion is kind of mind-blowing, but this is honestly, in my opinion, one of the most beautiful algorithms in computer science. You just say print the left tree, print my value, print the right tree, and it works. If you follow the route that it takes through the code, it's actually very complicated. I would not want to write that by hand, right? Go left, go up, go down, go up, go up, go up, go up, go right, go up, get it. I don't want to do that. You can probably do it with a stack. I mean, you can call it, because you're literally doing a stack when you do recursion, but trying to figure that out by hand, forget about it. It's really complicated. But when you take CSI 26, you'll be able to prove things like this correct. You start off by proving it to be true in the base case. Null pointer does nothing. With one node, print left does nothing, print right does nothing because they're null, and then it just prints you. So if you prove that it's true for the base case of size 1, then that allows you to write a proof saying, assume that it works for size n, prove that it works for size n plus 1. And so when you do that, you can just kind of assume that the left tree print works, and the right tree print works, and you just have to prove at the current level that if the left tree print and the right tree print work, that printing me in the middle is going to give a correct result, and it does, because you print everybody smaller than you, everybody bigger than you, and you have a proof that proves that this is correct for all sizes of trees and all shapes and forms and cases. And it is 27 problem worksheet, actually pretty fun. Inductive reasoning, proof by induction, yeah. When I took discrete math, it was 20 weeks of nothing but proofs, and I kind of boil it down a little bit in 26. The proof works because it's working. No, that's right. There you go. It works. All the numbers. Sorted. This is a sort algorithm, by the way. It just sorted all those numbers for me. Think about it, right? Because when you put numbers into a binary search tree, it's a log n, right? And if you put n numbers into a binary search tree, n numbers, log n work to insert for each one, n log n. It's actually a provably fastest sorting algorithm. Just insert all the values into a binary tree and print them. There you go. Sort. Right? Simple as that. This is a sorting algorithm. I don't even have a sort function anywhere in here. Just, right? I don't call sort. There's no sort anywhere in here. I'm just inserting values and then printing them, but it's sorting all those values that I inserted. Order n log n time, provably fastest. Assuming it's balanced, which it's not. Okay? So, let's talk about your homework assignment. For your homework assignment, There's kind of two steps to it. The first step is kind of reading the input and building a tree. So you're going to be building a binary tree of characters. So each node, its data is going to be a char, a single character. And other than that, it's probably going to be pretty similar to this. You're going to build the tree. You basically do insert. You can use my code. Feel free to plagiarize it as much as you want. Should be pretty similar to this. Build the tree. And then in the second phase of the program, the user is going to... It's like the Dungeon Delve game that I kind of ran you through last week. Basically, if the secret code is cat, then your code will be like go left, go right, hit the button, return back. Go left, hit the button, go back, go right, go left, go right, hit the button, go back. It's basically a spoiler. It's a problem solver for puzzles of the sort that were in my Dungeons & Dragons game 20 years ago. So that's search. The only difference is when you're searching, you need to print the steps you're taking as you go down. Take the left door, take the left door. Take the right door, take the left door. So you're going to start with this algorithm here and make kind of a verbose, noisy version of it that just basically says, I'm going to the left, I'm going to the right. And then you'll pass all the test cases. There you go, 5 points. Now, the second part is going to be a little bit trickier because in the second part, you're going to have to learn how to plagiarize. Okay, it's a very important skill in computer science. Now, computer science professors get really upset about cheating. And so the reason why we get upset about cheating is because if you just find a copy of Dungeon Delve online on Chegg or something like that, you just copy and paste it, you didn't learn anything. Right? The whole way to learn is you have to process these concepts in your head. Like you can't learn linked lists by copying and pasting other people's solutions. You can't learn linked lists or binary trees or anything with pointers until you sit down, you code it, and you cry, and there's like blood coming out of your ears as your brain starts leaking, various bodily fluids out of your ears. Like it's a process that every computer scientist goes through when encountering linked lists and binary search trees. And then basically when we finish, we just use the list class or the set class and never write our own again. Although occasionally we do. I shouldn't be quite so pessimistic. So, but this does teach you pointers. Like you have to sit there and go to the mental effort yourself to learn. And if you just copy and paste the solution, you don't learn. That said, how computer science works in practice is that we use other people's code all the time. And there's kind of a balancing act there. Okay. So for this assignment, I want your tears will flow like binary trees. Yeah, like seriously, like I don't let me downplay the difficulty of working with pointers. It's just a weird way of thinking. It's an extra level of indirection. Like you normally just have a variable, but now you have a pointer to a variable, right? And sometimes you have a pointer to a variable, and it's called a linked list. And it's like, all the levels of indirection get confusing, and that's why I tell you to sketch it out. And that's why for this assignment, you're going to be using bridges to visualize the binary search tree. Just like for Bridges Earthquake, I had you visualize the linked list for earthquakes. For this one, you're going to be using bridges to visualize a binary search tree. I want you to see your tree. And that's what Bridges was made for by the UNCC people, the University of North Carolina at Charlotte people. They made Bridges as a data structure visualization tool so that students, just like you in this class in data structures, who have trouble like with the pointers and like visualizing it in your head, you can actually just say like, hey, visualize my binary tree for me, and it'll show you. And you can look at it and be like, oh, I screwed up those pointers, didn't I? Like it'll actually show you what your binary tree looks like. And that's a really powerful thing. So for this assignment though, I have given you absolutely no starting code. I have not even given you a makefile that works, as one of you found out, all right? So how do you go? How do you start? Okay, so for Dungeon Delve, you're given a makefile. I added a hint here. But basically, I've given you a makefile that doesn't work. Okay, once you put bridges in. Okay? And so, like, how do you get it to work? Well, we did do Bridges Earthquake a second ago, right? Last week, Bridges Earthquake, remember that? I've graded them all already. I did that when I was in Rhode Island. And so if you look at the makefile for bridges earthquake, you'll see that little thing there. After main.cc -L curl. That's an L, not a 1. Okay. And I also use C++20. You might want to change that as well. You don't have to. I don't think there's anything in this assignment that needs C++20. But you can just copy this whole thing over if you wanted. Okay. How do I plagiarize respectfully? Well, first of all, you can always copy from yourself. I do a lot of like copying from my own makefiles, right? Like if I have a complicated makefile, I don't want to write this thing from scratch. You know what I mean? Like I don't want to write this from scratch. No, hell no. All these things and there's like, you know, I don't want to write it. No, hell no. I copy from myself all the time. So first of all, plagiarizing from yourself is more than welcome. And you already have one Bridges assignment under your belt. Use that. How do you type in your username and your API key? It's in the previous one. If you didn't do it, ask for help. We can help you if you didn't do the Bridges earthquake. Okay. Would it be viable to make a Vim macro for a makefile? You could. I just copy my old ones. It's really what it comes down to. And this makefile here is actually a pretty good general purpose makefile that just works on all projects that don't that contain a single project. Like all folders that contain a single project. If you've got different main.cc's in the same directory, it won't work. But if everything in the directory is for a project, for one executable, this is the only makefile you really need. So, okay, so let's talk dungeon delve. So, the fungeon. Yeah, so you're going to implement a BST, and then you're going to implement it again in Bridges. Or you could just use Bridges from the beginning. It's up to you. And for this assignment, I'm trying to teach you two things. How to read documentation, which is crucial. The only thing harder than reading documentation is writing documentation. I was just talking in the previous class about Microsoft, how Microsoft would promote people in part based on writing documentation. During the break, I was actually texting my friend who used to work for Microsoft, and he said that they no longer do that, but it's still kind of encouraged. So they have like a rubric that you're graded on, and one of the things you're graded on is producing documentation for your code. Because without that encouragement, programmers don't write documentation. We sort of hate it. We hate reading documentation. We hate writing documentation even more. It's something you sort of have to just get into the habit of doing and deal with it. Okay, so for this assignment, you're going to have to learn how to read documentation and how to steal source code. Okay, is this dungeon harder than Elden Ring dungeons? It's about the same. I'd say it's about the same. So stealing is kind of a dirty word. Like you're not supposed to steal. That said, steal from yourself. That's fine, right? I don't care. And also, you can steal from documentation. That's also fine. Just don't steal from each other, because if you just steal a completed work from your friend, you don't learn. Like you didn't go through the mental anguish necessary to transform you into a programmer, right? Like every programmer experiences the pain of like having your brain grabbed and like stretched out through the bones of your skull. It's like how the Can't Samurai Classroom Magic Sets suck. Right, man, Curly, do you know what I'm talking about? Like that feeling of like having your brain stretched. It's kind of a necessary experience to go through. If you never go through that, you're not gonna. I don't know. It's like in the Dune universe, the Sardaukar. There are these. They get sent to the prison planet, and they're put through a series of trials designed to test their mettle, and at the end of it, they become like the Emperor's elite fighting force. It's kind of like that. So, yeah, you should always like feel like your brain's getting stretched. Now, Bridges Earthquake wasn't designed to be that hard. Hopefully, that was just kind of straightforward. For this one, it should hurt your brain a little bit. So, let's take a look here. And you dying because you forgot a semicolon. Forgetting a semicolon is like one of the easiest things to deal with. Let's be real. There's way harder bugs to deal with than semicolons. So here we have documentation for Bridges. Okay, so binary search tree tutorial. It kind of explains how the binary trees work, and here's some starting code. Okay, so you can just go like this, and just copy it, and then paste that into your main, and just start there. Nothing wrong with that. Look, they use using namespace standard. So, yeah. And you got to punch in your assignment number, your user ID, your API key. You set the title, set the description, and then here they don't actually have any functions to build a binary search tree. You should probably write an insert function. You should probably write a search function to do that. What they have here, though, is they're just manually newing a bunch of nodes, and it's not like they don't know how to do it. They don't want to do it for you. They want you to go through the anguish. Okay. So yeah, I was talking to him. I met up with the Bridges people like 3 times or 4 times maybe at the conference. We had lunch 2 days ago, and had they're really good people. I really like them a lot. And we were talking about this stuff, and we're like, yeah, students need to get experience working with pointers, and like it's part of the process. You need to hit at least a certain level of basic familiarity with pointers, or you're just going to hose yourself in the future. Okay, so here they're just newing a bunch of elements and then just kind of manually linking the tree together. Okay. And they're showing you how to set a label on it, and this is how you bridges. Okay. So you say bridges set data structure root. That tells bridges the data structure you want to visualize. You do that, and then you call bridges.visualize. That's it. So this will take the pointer here in root, and it will draw it to the screen, and then they manually free up the memory. So it'll do something like this. Okay. And so that's what I want you to do. I want you to visualize your dungeon. You can either make your own tree class and do the assignment with the tree class, and then just you can like duplicate it in bridges, or you can use the bridges tree class from the beginning. It's up to you. It's your choice. Then they have more documentation on how to change the colors, change the size, change the shape. That should all look very familiar from last Friday. And you can see you can change the size and the color and the link visualizer. You can set the color on that as well, things like that. And then the final thing, I think, is just more of the same. Oh yeah, no, this is tree traversal here. So go left, go right. Okay. And so basically, do you see this? They're searching for 75, and they're kind of setting all of the links to be this bright blue color as they traverse the tree. So you can actually visualize your dungeon and then show like a route through it or something like that. And so with all the code here, copy, paste it, steal it. It's not cheating. That's what documentation is for. Documentation is there to be stolen from. Okay, that's why they put it out there. Okay. This is due on Friday. Mm-hmm. Yep. You should tell the New Mexico is pretty cool this time of year. No, they know that I'm in. They know that I'm in Fresno. They just didn't fix the video because they produced that a while ago. Yeah, I mean, if you think about it, like the entire computer science industry is based on people stealing from each other, right? In a good sense, you're right. Like the entire point of open source, free and open source, is that people publish their source code, and then other people look at the source code and learn from it. It's so much easier to learn. Like I learned bridges not by reading the documentation, but by looking at the source code examples. And I would look at the source code examples and be like, that's what I'm trying to do. That line right there is the thing that I'm looking for, and then I steal it, right? And so the bridges people sent me the teacher answers to things like bridges mountains and bridges earthquake and things like that. And I'd look at their code and be like, oh, I see what they're doing. Okay, all right, I understand it now. And looking at actual source code in practice is very, very valuable and very educational. And so that's what I'm trying to teach you on this assignment. Look at the documentation, look at example source code, adapt it to your needs. If you can do that, you're pretty much a programmer, okay? That's what it comes down to when you're a professional programmer, is you find examples of people out there that have done things that you've done before. You find the source code, you look at it, you're like, okay, that's what they're doing, but I need to change that. And so you copy it, you modify it to your own needs, and now you've got a working product. That's computer science in a nutshell. Nobody starts with a blank slate, you know? Like even if you start with like a blank main.cc, you still got the standard library. All that code's been written for you that you can use, right? You've still got the operating system Like, you're not starting from like a hard drive filled with zeros. Like, there's a lot of stuff you're standing on, right? All the work of all the C++ people over the years. So, yeah, exactly. Remember, it's the point of the standard library. Use functions that are already written, that are common, that are bug free as much as can be said. You know, like the entire growth of and the reason why computer science as a field has grown so much is because it's people standing on each other's shoulders going back to the 1970s, right? Like, you know, people share the source code, people learn from each other, and we sort of have collaboratively built this giant mountain of knowledge and experience and code that makes it possible for you as a second semester computer scientist to do really complicated things with very little effort, because it's all been done. Well, not all of it, but like a lot of the work's been done before. It's possible to write code without including anything. It is. That's a valid program. That's valid C++. Does nothing successfully. Returns 0. Returns 42. No includes. Not very useful, but it's not useful, but okay. It's visualize it. Imagine trying to write all the libraries needed in a single file. Yeah, it's thousands of lines of code that have been debugged and tested and optimized. And, yeah. Is there anything useful you can do without including? What do you mean? I just returned 42. I returned 0. What are you talking about? I mean, that's not useful. So it's cool if we use as much of your BSD file as you need to? Yeah, so absolutely. So I put it up in public. I think it's called Delve. I've got Delve Hints. Yeah. So it's up in public Delve Hints. So that's... there's that. There's public. Yeah, copy all you want. You have my blessing. That's a full implementation. Remind me on Wednesday, we need to talk about deleting. I talked about that in person, and I didn't talk about it with you. So I need to talk about that because we're kind of out of time already. So we need to talk about deleting from a tree, because that's the worst part. The deleting from a tree, you can see it's like, it's a thing. It's a whole thing. 158 lines. It's 57 lines of code to delete. Right. Whereas searching is 8 or so. Okay. So feel free to steal as much of my source code as you want. Just get the job done. Don't steal from each other though. You know what I mean? Like don't copy code from your friends, like, because then you risk just not doing anything. Right. So, all right. Doesn't sound too important. Can wait till Wednesday. I would start now. I would start now. Try and get the first half done by Wednesday. You can ask me for questions. There is no delete, by the way, in the homework assignment. I will talk about delete on Wednesday, but you don't need it for the homework assignment. All you need is insert and search. That's it. Okay. So technically, this is no longer a greenfield assignment. You have extra stuff. So I gave you blank files. So you need to figure out the make file. You need to figure out everything, kind of. But that will involve copying chunks of code, like a real programmer. I'm trying to give you the real programmer experience. So also on Wednesday, I think we're going to do some job interview questions. We don't have time really to get into it now. We're already out of time. But in the previous class, I was talking a lot about the hiring market right now is very hot. And there is a hiring fair for C++ programmers next Tuesday and Wednesday online. And you can possibly get a job as a junior programmer or something like that, fully remote from Fresno. It's a brave new world. It used to be you'd have to go to San Francisco and pay $4,000 a month for a 2-bedroom. We were looking it up in the previous class. Take-home pay as a starting programmer at Microsoft's about $148,000 a year. Sorry, that's not take-home. You lose about half that, right? So you take home about 80 or so, and then of the 80, about 50 goes to your house and power and water. So you're living on $30,000 a year. And you got to have the car, and you got to have food. And you're basically living in poverty, you know, on $150,000 a year in the Bay Area. So, and something like that. And Kearney should give 1 unit 4 to 6 week course on job interview preparation. I think we're going to do that on Wednesday. I kind of want to just do some like quick job interview like problems with you. You can code live. I'll give you a few minutes to think about it, and then maybe I'll answer some questions. We do need to talk about delete, but maybe on Wednesday and Friday we'll do some quick extra credit, maybe 4 credit stuff where we're just practicing like job interview questions and things like that. Yeah, after 100K taxes get crazy. Yeah, the bracket is quite high, and taxes don't take into account cost of living, right? And so it's really rough, right? Like to live on $30,000 a year when you thought you're making 150, right? So you get a roommate, you know, or you get married to somebody and pool your money while living in an apartment, trying to save up for a house, things like that. Okay. Yeah, but the good news is with remote work, you can work out of Fresno, you know. It's the thing. All right, that's enough. We will pick that up on Wednesday. I will be, I guess, streaming Elden Ring now because there was some requests for that. So hang out if you want to watch me play Elden Ring for, I don't know, half an hour or so. Probably spare. All right, thanks everyone. See you then.